In this final video for chapter 18, we're going to talk just kind of briefly about heat transfer. And heat transfer can occur basically by three different methods. So we'll start first with conduction. Conduction is the transfer of heat just by direct contact. Again, heat transfer can occur really only due to a temperature difference between two things. So when I talk about direct contact, I mean, for example, that you have a slab of material that's colder on one side than the other. So you could, do this, for example, with a wall. It's colder in your house and hotter outside. Well, heat will transfer from the hot to the cold side. So the heat will actually flow through the material from the hot temperature to the cold. Now, the rate of energy transfer through this slab depends on a couple of things, properties of the slab of material. First thing that it depends on is what the material is made of. And so there's a constant K called the thermal conductivity, which will depend on the material that you have. Now, there is a table in the book, I think, with different thermal conductivities. Now, as it turns out, again, you can do kind of an empirical measurement of this by testing different materials. What you find is that the rate, P con here, or heat over time, depends on the thermal conductivity, what material it is. The bigger the K, the faster the heat will flow. The area of the slab, by that I mean the cross-sectional area here of this side. But then it also depends on the size of the temperature difference, right? If you have a really hot outside, the heat's going to flow faster than if it's just a minor temperature difference. It also depends on the thickness of the slab. So L here, I mean how thick the material is, right? The thicker the wall, the slower the heat is going to actually transfer through it. So this is the formula that you can use to solve the problem in the chapter 18 homework. It's also, in my class, the lab focuses on these relationships. One thing to notice about this is that this is similar to Ohm's law, right? If you identify that the rate of heat conduction, Q over T, is similar to electric current, I, and the temperature difference, TH minus TC, is similar to the voltage, or EMF, right? It's what's driving the heat flow. And then L over Ka, just the inverse of Ka over L here, is similar to the resistance in electric circuits. In fact, we might call this the thermal resistance, or sometimes if you go to buy insulation, you'll see the R value. And that's really this, it's the thermal resistance of the material. So if you remember, right, voltage equals current times resistance. Well, temperature difference equals rate of heat conduction times the thermal resistance. So again, it is very similar in a lot of ways, and we will actually see heat transfer similar to electric current in other ways as well. So conduction is one method of transferring heat. We have two others. One of the others is radiation, which is energy transfer via the emission or absorption of electromagnetic energy. So for example, if you go out on a sunny day, you are absorbing radiation, light, which is really an electromagnetic wave. You're absorbing heat from that sunlight, and your temperature will generally rise. The sun, on the other hand, is emitting heat, right, or emitting radiation, electromagnetic waves, due to its temperature. And there's a law that can describe this emission or actually absorption of heat for certain objects called the Stefan-Boltzmann law. I'm not going to go into great detail on this, but what we find is that these radiative objects like the sun emit heat proportional to the fourth power of the temperature. There's also a constant that's involved, which is called the Stefan-Boltzmann constant. And there's the emissivity of the material, right? If it's a perfect emitter, this E or epsilon will equal 1. It's also related to the surface area, A, of the sun or whatever material is emitting the radiation. So again, I'm not going to go into great detail on this. The one thing that's interesting is studying thermodynamic problems involving radiation was really the starting point of quantum mechanics. So when we get to Physics 223, we might come back to discussing radiation energy transfer through electromagnetic waves. The third way of transferring energy is just due to a temperature difference that causes an energy transfer through a fluid, right? So for example, if you have your convection oven, you've got a hot heating element, it's going to heat the air in the oven, and that air is going to move, and that will transfer energy to your food through the air or the fluid. So convection occurs right on the earth. If the air or the ground gets hot from the sunlight, it'll heat the air above it. You'll get air currents. Any type of heat transfer that way through a fluid we call convection.